What's up, everyone? We are now on 8.5. We're going to be looking at finding the area of regular polygons. Now, this lesson is actually technically split into two separate lessons. This first lesson, we're going to be finding the area of regular polygons without trigonometry. Next time, we're going to be doing it with trigonometry. So stay tuned. So first things first, take a look here. Notice that with my shape, whatever polygon you have, you can always circumscribe a circle around it. So this circumscribing just means, hey, I can draw a circle such that it touches the edges, and by the edges I mean the corners of your shape exactly once. That's what it means to circumscribe. Now there are a few things we can label in this figure. First off, we know that the center of a regular polygon is also the center of the circumscribed circle. So then this gives us two things that we can draw. So we can draw the radius, which if you remember, the radius is the distance from the center of a circle to the edge of a circle. Well, in this case, all the edges of the edges of the polygons meet at the edge of the circle, which we call the vertex. So this right here would be a radius. And so likewise, I can draw another one here. There's my other radius. And then, of course, I should probably label my center. Now you're going to learn a new word here. The blank is the perpendicular distance from the center to a side. So what we're talking about is this line here from the center to the middle of one of your sides. This line right here, we call the apothem. So this line does something special to the side of your shape. It splits it into two equal parts. And that's going to be very important for this lesson. So you got to know this. Oh, and also just another quick reminder that your triangle there that you've created is a right triangle. So that means you can either have a special right triangle, or you may need the Pythagorean theorem, or in next lesson, you will need trigonometry. So first off, here's our regular pentagon with the radii in the blue dots and our apothem with the red dotted line. I wish for us to find the measure of each of these numbered angles. I've kind of given you a little hint here. Go ahead and try it if you think you can. Otherwise, just hold on and we'll work it through together. Okay, so first off, angle 1 is considered a central angle. So finding angle 1, I have to do 360 divided by the number of sides that I have. Well, seeing as how this is a pentagon, I know that I'm going to have 5 sides. So, my central angle, which is angle 1, equals 360 divided by 5, which will be 72 degrees. Now notice that angle 2 lies nested inside of this triangle here. And remember we said earlier that the apothem, the red dotted line, splits these two sides into equal parts. Well, coincidentally, it also splits these into two equal parts. So we had calculated angle 1 already, which is the same in each of those 5 sectors. So angle 2 is simply going to be the measure of angle 1 split in half, which I believe gets us our 36 degrees. If I can write that correctly. Thank you. 36 degrees. Now, angle 3 notice that that's inside of that smaller triangle right here. So all those angles have to add up to 180. One of our angles we just found was 36. The other one is 90. So angle 3 is going to be found by adding it with the 90 and our 36, and then eventually subtracting it from 180. So angle 3 plus 126 equals 180. I'm going to take away 126 from both sides. So therefore angle 3 will equal 54 degrees. Now this is going to be very important for you to be able to do, especially when we get into the trigonometry section. For now, it's going to be, kind of crucial that you start mastering this. You want to get good at it so that you can recognize whether you're going to need trig, special right triangle, or if you're just going to need the Pythagorean theorem. Now right here on example 2, we're going to find the area of this regular hexagon, and what we have done is we've unrolled this hexagon to make it into triangles. We know the formula for finding the area of a triangle. We know that that's 1/2 base times height. Well, thankfully for us, the base length is 6, the height is 5. So all I do is plug this into my formula. 1/2 of 6 times 5, which gets us 15. But hold on, that's the area of one triangle. Inside of a hexagon, I was able to split it into 6 equal pieces. Here are the 6 triangles. So realistically, what I'm doing is I'm going to multiply my formula by the number of sides there are. So right here I have 15 times 6, which gets us our 90. So this hexagon has an area of 90 inches squared. Now I want to do a little bit of work here to prove to you and show you the derivation of your new formula for finding the area of regular polygons. So going back to this, notice that that 6 represented one part of the side of your hexagon. Well, if I were to highlight that entire base, all those bases right there, they would go all the way around my hexagon. Well, if you remember that we can sort of rewrite our expression as saying, well, I have 6 triangles times our formula. 1/2 base times height. Well, in the figure, the height represented the apothem. So I'm going to replace h with a. And 6 times my base length actually gives me the perimeter. The perimeter of my entire hexagon was found by the number of sides that I had times the length of one of those sides. So that is the same thing as our perimeter, which I'm going to write right here. There's nothing I can do to simplify the 1/2, so I keep that. And there we go. That is our formula for finding the area of any regular hexagon or octagon, nonagon, whatever polygon you want, you can use that formula. We say 1/2 AP. Now, I do capitalize the P because it is the perimeter of our shape. There's my perimeter. You add up all your sides. Your apothem, remember again, is the length from the center, the distance from the center, straight to the middle of another side. And the 1/2 comes from the area of a triangle formula. So at this point, it's good to know that there will be several instances where you are missing information. You will have to use all prior information you have to find those missing pieces and to eventually help you use those triangles that are inside of your polygon. So I'm going to stop the video now so that I don't rush the next part. We're going to go ahead and do part 2, which is the backside. But before I do, it'd be good to note that we can use the formula right away on example 3. So first off, I tell you what shape you're given. Decagon. So I'm automatically thinking, I know how many sides this is. Deca stands for 10. So I have 10 sides. Now it says I have a 6-inch apothem, and I have a side length of 8 inches. So visually, it'd be a little hard to draw a 10-sided shape. So I'm just going to simplify the idea to one tiny portion of it. So my apothem will go from the center here straight down to the side. So there's my 6 inches. And I'm told that the side length is 8 inches. Well, the only thing I really need is the perimeter. And since I know how long each side is and how many sides there are, my perimeter will equal 10 times 8. Well, now we're ready to go. The area is going to equal 1/2 apothem times perimeter. I'm going to move that over here, give me a little more room. Well, we're going to take 1/2 of our apothem, which was 6, times our perimeter, which was 80. So plug and chug, you should get 240. Now again, going back to the units, they're in inches. And since I'm finding area, we're looking at inches squared.